Okay, this is the second truss problem I think I gave you. Okay, so here it is. Now, I don't know how easy it is to read, but this is joint A down here, joint B at the top, joint C on the right-hand side. This is a 90-degree right triangle with 45-degree other two angles. So the first step is going to be to determine the support reactions, the reactive forces at the supports. So A is pinned and C is rolling. I don't know if that's obvious. It's kind of hard to see this one, but this is like a hinge, and this one is a hinge, but it has these little slidey roller thing down here. So I don't know how easy this figure is to read, but pinned implies that there are horizontal forces and vertical reactive forces, so we can draw those here. And a rolling support means that there's only vertical forces because it's allowed to move in the horizontal direction. So A is going to have two support reactions. C is going to have one support reaction. And of course, we have the overall external applied force of 500 pounds to the right. So the sum of the forces is 0. The sum of the moments is 0. Those are our conditions for static determinacy. We're going to start with this condition that the sum of the moments is 0. And we're going to figure out what are the torques, what are the moments on this system. So that means the clockwise torque and the counterclockwise torque are going to, the sum of those is going to be 0. So we're going to look at the clockwise and the counterclockwise. So the clockwise torque is going to be given by the external load in this case. I'm choosing point A, joint A as my pivot. And so this external applied force to the right is going to cause this whole system to want to torque or turn clockwise. And that's this going to be this torque. And then the counterclockwise torque is going to be caused by the reactive force at joint C. So you know, therefore, that joint C must be pushing up because that's the only way to get a counterclockwise torque. Now, the first torque is going to be, if from our pivot to the force, is 10 feet times 500 pounds, so that's 5,000 foot-pounds. And the other torque, again, along the same line as our torque arm, is 10 feet times this reactive force at support C. And so here we're just solving for the force at C, which is going to be 500 pounds. Now we can solve for the force at A because we know the sum of the forces must equal 0. These are both in the y direction, so the reactive force at A in the y direction, AY, is going to be equal to also 500 pounds. So AY plus CY equals 0, which means CY is 500 pounds, which means AY is negative 500 pounds. Remember, the negative sign just means that arrow points down, which means I should erase it and make it go in the other direction. All right, so that's here. So this one goes up. AY must go down, negative 500, because they have to negate each other. Now, the other reactive force at joint A is the horizontal force, and that is going to balance with the 500-pound horizontal force that is the external applied force at joint B. Okay, so we need to figure out the horizontal force at A, and so that's going to negate the external applied force, which is applied at B. And so you know that this force, and I've drawn it toward the joint just by convention, but now I realize it must go away from the joint, right, because they have to offset each other. So I know that this must be negative 500 pounds because this external applied force is positive 500 pounds to the right is positive, to the left is negative. So these are my three support forces, right? Now, I'm going to use those, and I'm going to start with joint A, and I'm going to look at all the forces that are applied at joint A. So there is a horizontal support force because it's pinned, and there is a vertical support force, and then there are also the forces within the members. And so one thing that's kind of important that I'll try to say over and over again is that the members can only apply or have force in the direction that they exist in. So we're going to add all of our forces here. We know that the left-hand reactive force is negative 500 pounds, which means that this other force that's supplied from AC, the member AC, that must, because they are the only two horizontal forces, that must be 500 pounds. And so that means because AX here, negative 500 pounds, plus a FAC, which is only in the X dimension, they must equal 0, therefore FAC must be 500. Okay, now I can't remember where I was here. All right, so we have FAC is 500 pounds, right? So that's this lower member here. And then if we think about tension or compression, the arrow here is facing away from the joint, which means the other arrow here will be facing away from the joint, which means the internal forces in the member will face toward those arrows. Think about it as active and reactive forces, right? So this is the joint. This is the joint. The arrows face away, which means the member faces out, which is tension. So we know that's a tension member. All right, let's erase this. When we think about tension and compression, it's good if you can think about what will happen. Remember to think about it as what happens if I take my little structure, whatever it is, and the blue arrow, remember, is the force, the external force. If I pull on that and then I remove a member just all at once, what happens to the structure? So I'm going to remove member BC. And I think what's going to happen is this structure is just going to collapse, right, like this. And that implies that member BC is under compression because it's squishing together. Now if we do the same thing and instead I remove AB, then I think what's going to happen is it's just going to open up, right? It's going to open up into a big structure like this. So I think that that means that AB is under tension. And if instead we remove AC, which is the bottom member, I'm going to do that with a green arrow, we're going to remove this one. So remember we have our original triangle and I remove that. I think what's going to happen is I think this whole structure is just going to pull forward. So I think that means that member AC is under tension, which does match what we said here. Okay. So tension, and that's again what, whenever the arrows point away from the joint, that means that that member is under tension. So when you write the answer, you're going to write FAC force is 500 pounds, and then you're going to put like a T in parentheses for tension. Now we're going to erase all this, and we're going to go to a different joint. We have our external forces. So now we're going to do AB. Actually, we're going to stay at the same joint A, but we still need to do member AB. So now the Y, so if we look at the forces here at joint A, there's only two forces that have vertical components, right? The one straight along member AB, so that would be FAB, is purely Y component, and that's going to be opposed to the negative 500 pound reactive external force that we figured out in the first step. So that means that the magnitude of FAB is 500 pounds and it points straight up. So we actually don't need to do anything else other than figure out tension and compression. If the arrows point away from the joint, that means that the reactive arrows point outward, which is tension, and that matches what we said in the first part when we figured out that this member must be under tension, because when we take it away and we pull forward, it's going to separate. So now we've done the two members, the two legs, and then the last one we need to do is this hypotenuse member. Member BC, so we need to move to a different joint. You could pick B or C. Looks like I picked B, but you could pick C. You probably have enough information to answer it that way too. So the external force I'm drawing with the gray arrow, and then the other two forces are along the members. We already know AB is 500 pounds because we answered that just a few minutes ago. We know that it points away, right, because it pointed away on this side. This member's under tension, so it has to point away from the joint. And so that means that because this one points down, this one must point up. Member BC must be going in this direction, right, toward the joint B. So we're going to figure out FBC, but we do know which direction it points. We also know this angle must be 45 degrees because this angle is 45 and this is a right triangle. So if we think about FBC, it has an X component and a Y component. The sum of the forces along X must equal 0. So we have this external force, 500 pounds, pulling out, which means that the other X component, which is the X component of BC, it's the only other horizontal component at joint B, right? So there's this downward, which is FAB. It has no X component though, so we can ignore that, and we can say that we know this 500-pound external force must be equalized by the X component of BC, of that BC vector. So they must be equal to each other. So we know FBC X must equal negative 500. The negative just indicates it points to the left, and that doesn't really matter because we're going to use that X component to figure out what BC actually represents. What's the magnitude of this force, right? So we do know what I'm drawing here is a blue arrow. We know that it points to the left because it has to negate the external force, which points to the right. So if it points to the left, because this member is going this direction, that means it's pointing left and up, right? And so we also know that it points left and up. We can automatically say that that must be under compression. But let's figure out what it is first. So we have a Y component and an X component. Here I'm showing you that this is compression, which we'll write at the end, but we still haven't figured out the magnitude of this yet. So the magnitude is going to be related to this angle. So we have a 45-degree angle here. This black here is the same as the black there. And so we're going to try to find FBC by relating it to what we know down here, which is FBX. So this is the opposite side, and this is the hypotenuse. So the sine of 45 degrees is equal to FBCX, which we know is 500, divided by FBC. So we're going to solve for FBC. It's going to equal 500 divided by the sine of 45, which is 707 pounds. And we already know it is under compression. So I would write a C in parentheses because I already figured that out. And that's what that's telling you there. This little bar down here is in the way. But this says tension or compression. So this negative sign that was here, that just told me that it pointed to the left. That doesn't really matter anymore because I'm going to say that this member is under compression. So you give the magnitude of the force and then T or C to indicate tension or compression. You leave the sign off. All right, so here's to summarize. FAC is 500 pounds in tension, FAB is 500 pounds in tension, and FBC is 707 pounds in compression. Let me know if that is unclear.